I'm Professor David Harwood.
Appreciate it.
Sure thing.
Hey, everybody. Good to see you. I really appreciate the invitation to come in and talk to you about a series of projects, but a big initiative that Mindy Searles and I and others on campus here are putting forward, which, as Ken said, was to repurpose an abandoned death missile silo in Seward. So I want to kind of focus on that in general, but I want to give you some other background information just about climate science, about ice core science, about work that we've been doing and are continuing to do within Antarctica. So you're going to get a little bit of background on the Antarctic ice sheet, about climate, the record that's come from ice cores, and in part the need for better tools, right? So oftentimes we will go out and drill in remote areas without the tools being the best tested or the best prepared. We really need a center where we can design while we are building, where we can test, where we can do things we couldn't perceive to do without this kind of a facility. So this is also part of a university's grand challenge program. The university came up with $40 million over 4 years to invest in large scale, bold projects. The one that we're promoting here and we're funded to help develop this was an ice coring and education, or ICE silo. And I like the tagline in here in some way: cold region science and education in a Cold War facility. We also have another play on words that goes with this about using repurposing Cold War infrastructure to battle the warm war, right? The understanding of climate change, our warming world, to be able to better predict what the future will be in terms of size of ice sheet changes and the resulting sea level rise, but also the rate of some of those changes. So I'm a geologist. I work in the past time, right? I travel in my mind to different time periods based on the rock records I'm looking at. And in times, the Earth has been in different states, whether there are ice sheets in the northern hemisphere and sea level is about 180 feet lower when those ice sheets are there, or today where they are, or in the future and in the past when the Antarctic ice sheets melted or will melt in the future. What's that rate of sea level rise? And of course, that all feeds into policymakers and economists and others that try to project and predict some of the future here. So I'm also happy to promote and applaud the effort of the ice drilling group here. Jim McManus has been building ice drills for quite some time. Myself, Jim, and Dennis Dooling kind of serve as a central core of this hot water drilling group. And UNL has 3 different hot water drilling systems. So using these hot water drilling systems to be able to make holes into the ice to access the subglacial environment in subglacial lakes, for example, or to, with this smaller system here, to put in, dynamite or blasting shot holes to do some geophysics, or to recover other cores. So it's kind of a unique system. This system is a clean access one. I'll show you a picture later of this, but basically all of these shipping containers through here is part of the University of Nebraska's hot water drilling system. It's a clean access system, so it is ultra filtered, and also with ultraviolet radiation, nothing is going to be contaminating the subglacial environment. And here you see a number of the drillers and engineers that worked on these various projects through time. A few years ago, before COVID, the UNL's drill team and myself went down to this area of West Antarctica, and with this system melted down this distance into subglacial Lake Mercer, which is about the size of 2 Lake McConaughey's, about 15 meters deep, but it's part of the aquatic system that exists underneath the ice sheet. The funding for this project was to really understand microbial ecosystems in this environment. Where are they getting their carbon? How are they growing? That was the fundamental driver for this. But also along with that, anytime you enter into a subglacial environment or try to understand the nature of that region that we can't really perceive, it's really important to get boundary conditions, if you will, for the numerical models, right? And an overarching maybe approach and theme to the work that I do going back in time is we can interpret by reading ice cores or reading rock cores, sediment cores, fossils back in time. We can interpret what has happened to that region in the past. And then having numerical models be tested against that historical record to show if they can repeat the history that we know happened by our drill cores. Often they fail, but they need to be tweaked, need to be revised, and then they get better. So they are fine-tuned and advanced by being tested against the past record. If they can adequately backcast the record, they can responsibly forecast the record in terms of rates and whatever change. So that would be part of my 3-minute speech in an elevator with someone as to why this work is kind of important. So I'm kind of jumping ahead here a little bit. This is our overall plan, is to turn an abandoned Atlas F missile silo. There's actually 12 of them around Lincoln. Lincoln Air Force Base was very active during the Cold War with aircraft, like Dr. Strangelove kind of approaches, but also there were 12 of these around Lincoln. And our goal here is to use that abandoned hole in the ground to do some interesting work. So I just want to advance beyond this, but give you a scope of what we're trying to do here is to build a world-class and much needed facility to test drills, to develop drills, to make University of Nebraska Lincoln be even more at the front, cutting edge, if you will, of ice drilling technology. And this facility would be used by many nations who are doing this as well. And in particular, if you can have a facility like this be the center where other drilling tools are certified to be able to access these subglacial environments, right? So how clean is clean? Well, how are you going to know that, right? But maybe this is a way to do that. And if we wanted to sustain activity on this site, it would be to get with the international regulatory group, if you will, the Scientific Committee for Antarctic Research, to find some way to do that. So I want to share with you first a quick video. As part of the Grand Challenges program, it's been really interesting to engage with folks across campus. Folks from 6 different colleges on the UNL campus are engaged in this. The College of Fine and Performing Arts here and the Johnny Carson Center for Emerging Arts are engaged in this, of how to use this facility, not just for the science drilling, but also for broad education and outreach and science literacy components. So Ash Eliza Smith here produced this video, which is going to be released here pretty soon across campus, to kind of give a sense about what the silo is, what it could be. And again, hopefully this will be a bit of background for you as I continue with this. This is also in conjunction with the College of Architecture. Brian Kelly is actually his research area, repurposing and Atlas F missile society. This is from us, but also from the architecture complex that have the same focus.
Essentially, we're an interdisciplinary team using technology and collaborative storytelling methods across architecture and emerging media arts as a way to bring in the past and help shape the future. We work between the physical into the digital and vice versa. Currently, we're using LiDAR scans, photogrammetry via drone capture that Rogue out of Kansas City captured. We are also experimenting with NERFs, neural radiance fields, real-time 3D technologies, in addition to 2D video and images. Essentially, we're trying to create a new language, collage of different storytelling methods.
So you can see my little cursor here flying. The little white line there is a path, so you can see the zigzag I flew before. It's currently flying, I don't like to zoom out over here, to the green dot to start its path. There's its current view.
We can create 3D meshes or things along that line, but we could still do several hundred acres fairly quickly and generate topos and contour maps. We typically are doing buildings, so a lot smaller area, but being able to do that in a very rapid or short amount of time as opposed to what we can do with a laser scanner.
I'm Ashaliza Smith. I work here at the Johnny Carson Center for Emerging Media Arts, and I run a lab here that has a working group that focuses on expanded realities, thinking about spatial storytelling and locative media. Our team compromises land use planners, placemakers, architects, engineers, community members, scholars, and artists, creators. And one of our primary goals is to think about how to go beyond a digital twin of a site to create interactive stories. The extraordinary history of the missile silo, combined with its repurposed objectives, will also provide novel opportunities for engagement, education, and tourism.
My name is Brian Kelly. I'm an associate professor of architecture in the College of Architecture. And one of my research agendas is into the abandoned Atlas F Cold War missile silos, and specifically looking at the construction of them and the ways in which they had to kind of overcome some pretty major hurdles to be able to get them built. I'm using contemporary imaging technology, photogrammetry and LiDAR, to then be able to document the way that they sit right now and comparing that to the way that they were intended to be built through the archival documents from the 1960s, or the construction documents. So with Rogue Visual Design, we used the LiDAR to then understand exactly dimensionally what the building looked like, and its exact sizing and things like that. They would use that then to, well, first of all, visualize the project, but then to be able to verify whether or not their designs fit within the existing space, and then to build a complete and accurate set of as-builts for it.
One of the main reasons why we need a facility like this is that typically if you wanted to do drilling down in Antarctica, you need to be able to test your equipment. Currently what they do is that they either drill into a really, really small test hole that they have, or else they pay to fly all the equipment up into the Arctic regions, Alaska, places like that, in order to drill into the ice there. This would allow us to design an ice column that you can kind of personalize to test new places. The way we want to design this ice column is we want to be able to have things like fresh ice or dirty ice, or maybe even drill into some water. So we can customize that ice column to be able to explore places that haven't been explored in Antarctica yet.
So the university's had a really long history of ice drilling as a result of some collaboration. It goes back into the to the 70s and 80s and 90s with Polar Ice Coring Office, with the Ross Ice drilling project back through here. So this would be like the next step to sustain a lot of the prior research and technological development supporting researchers in the polar regions that would be held here at University of Nebraska to be able to continue that legacy. So the University of Nebraska could stand out as a leader in ice drilling equipment technology because we could design while we're testing and really get things right. We're probably looking 3, 4, perhaps 8 years down the track if everything goes well. And the beauty of a lot of this is that it's not just the ice drilling test facility, but there's so many broader portions of this as well that come with Cold War history, the legacy of the missileers that worked in these, plus an opportunity in an education mode to use this unique facility for education, to bring climate change research to the front, to bring drilling technology, which also impacts folks here in Nebraska with irrigation wells, et cetera. So it's a kind of a broad opportunity to expand the university's reach with this facility, and to really integrate across campus entities a single purpose here to the benefit of Nebraskans, the nation, and the world. So just some background about why this kind of facility is needed. Why do it? What's the urgency? What information can we gain? And it really comes to that line of improving numerical model predictions. This figure right over here scares me a lot. What it's showing is the drainage sectors, drainage basins, if you will, of the Antarctic ice sheet over here. And on this side over here, it's showing those same drainage basins, but each dot is reflecting the volume of ice that is being lost in terms of gigatons. You can see that some areas, particularly West Antarctica over here, are losing an awful lot of ice, very, very focused in that. It's chiefly the Thwaites Glacier and the Pine Island Glacier here that are just excavating, right? So what's the process for that? How can our models show that and predict some things? We also see some sectors over here that are showing, more loss of ice, and I'll show you why that is as well. But the part that's scary about this to me is the ocean heat. What you're seeing out here is the temperature of the ocean 3 football fields down. All right. The surface of Antarctica is really cold, has sea ice that grows on it every season. It freezes, it expands and retreats through that. It's really cold. It's, around freezing. So close to Antarctica, it's around these temperatures at the surface, but just 300 meters down below, it's, upward of 2 degrees C. So you have about 4 degrees or so of temperature just with depth. And that is pretty dangerous, I think. The North Atlantic deep water comes up, circumpolar deep water comes up through here. Warm waters are at the edge of the Antarctic ice sheet, right? So there's enough heat to melt all that. The models, there was a project I was associated with or leading, the Andril project, drilling deep into time. And the models at the time could not make the ice sheet go away. They could not give us the dynamic behavior we were seeing in the ice cores until you added in ocean heat. Right. And that was just 15 years ago that the models changed fundamentally by adding that ocean heat as a component that drives the ice sheets coming and going. And now all the focus is on that. But it's a part of the Earth system around Antarctica that we're not monitoring right now. So it's really an unstable condition here with these marine-based ice sheets where the ice actually is grounded below sea level and it's grounded with a reverse slope towards the continent. And the chance for these warm waters to make their way up underneath the ice cavity and into this reverse grade slope here. It's conditions for catastrophe of rapid collapse of these ice sheets. And of course, that has an implication not just for our climate as such, but really for sea level. You can see in each of these sectors as well, I was just talking about, they're kind of summarized through here, but these represent meters of sea level component for these different parts of it. So West Antarctica has about 5 meters of sea level rise. Potential East Antarctica has maybe 50 to 60 meters of sea level rise. So that's a big impact. And it's not just an impact in terms of changing coastlines, but it's about displacing people, right, in the future, what it's going to take to do this. So this is Antarctica. I want to quickly just introduce you to it. High elevation area in East Antarctica, 4 kilometers high through here. West Antarctica, much lower, but it's also different in being grounded well below sea level. Very deep basins in here, 1,300 meters or so in some of these basins of West Antarctica. Whereas much of East Antarctica is above sea level, there are still some marine embayments that would be through there. So this is if you removed all the ice. This is what Antarctica would look like. 2 different ice sheets as well. The West Antarctic ice sheet's much lower. East Antarctic ice sheet's a lot higher. And by being higher, it's up into the higher part of the atmosphere. So it's colder. The ice and snowfall up here is much colder. But I'm thinking about this with drilling through this. And our major revolution in climate science came with the advent of ice core drilling to drill through the Antarctic ice sheet down to some level, to drill down through the West Antarctic ice sheet as well, to get that past history in 2 ways, right? So the ice, hydrogen and oxygen, H2O, and isotopes of those, they actually can be used, their ratios, to tell temperature, right? Fractionation of that temperature. So we get a past record. If you look down through the ice cores through time, you get a past record of temperature change. But because the snow that falls gets buried and trapped and it captures bubbles of ice, you can see through here that these the ice cores actually provide an archive of the ancient atmosphere as well, really fundamental thing, right? So if you take a sample of any of these ice cores, stick it in a vacuum chamber, suck out all the air, melt that ice, what you're then measuring is the ancient air. And this is the history from the longest ice core record from the top of the Antarctic ice sheet. The epic ice core record goes back about 800,000 years. It goes back through 8 or so different glacial interglacial cycles, which show a rapid rise to interglacial conditions, back to a glaciation, rapid rise to an interglacial, et cetera, this pattern, right? And we would expect to see in the future, going into the next glaciation based on this history. This is all, the pacing of this is driven by changes in the shape of the Earth's orbit, right? Eccentricity, basically on this 100,000 year scale through here. But we're kind of out of the box right now because we are presently, nature has balanced the CO2 levels pretty well. And today we're way outside of that box, basically. Yeah. So sea level change, which is also there, is driven by the changes in the extent and thickness of these different ice sheets as they come and go through that climate record. And the modeling that we have done has shown with atmospheric carbon dioxide levels that have gone through the ice core record from 180 parts per million up to 280. And this has been the pacing and the driving force through greenhouse gas effect of driving those glacial interglacial cycles of the Northern Hemisphere ice sheets expanding across into lower latitudes or retreating has been this pattern. By the drilling we did with the Andrill project, the models show that once we get to 400 or so parts per million, that the Western Arctic ice sheet is vulnerable. Okay. Anybody know where we are right now in terms of atmospheric carbon dioxide levels? We're about 420. Okay, so we are here. The models are showing us that we have already bought the absence of the Western Antarctic ice sheet. But what we need to know is, can we reverse it, right? Perhaps. But how fast is it going to change? Which sectors of the Antarctic ice sheet are going to be most vulnerable? That's what we're trying to get at. Our models also project that if CO2 levels rise up to 750 parts per million, that's the model threshold for when you could not have ice sheets in Antarctica, right? And we're rising pretty quickly through here. So a little bit of background of some of the geological research I've been doing, my colleagues have been doing. It's trying to figure out the marine history of West Antarctica, right? Of this part of a rifted part of West Antarctica that has marine sediments in it. And I use these microfossils to tell past times when there were seas across Antarctica, when it looked something like this. This red line right here represents a cross section through the Ross Embayment and gives you a sense of the sampling that we've done to date. So there's a volcanic island out here, Ross Island, floating ice shelf through here. And these are the points where we've melted down through the ice and taken some samples. Some of those samples are just short tagging of sediment cores through here by melting through there. The Andrill record, we drilled very deeply in this moat produced by this volcanic island through here. That's a great record. This year, November, December, we are going to drill at this site, maybe drill 200 meters. Up here. And then next year, we're going to drill at this site 200 meters as well to try to better interpret the history of the center part of West Antarctica. Of course, as that video mentioned, Nebraska has been involved in ice core drilling and Antarctic research for quite some time. This is in the 70s through here. The first penetration into a submarine cavity beneath an ice shelf was the Ross Ice Shelf project through here. From looking at cores taken in that area and looking at the diatoms that I've examined in there, I can identify that there are 3 different ages of when there were marine seas across West Antarctica. There are probably more. The past history is important, but what we're really looking for is this younger history, right? Because it's the younger history that's going to drive a better understanding of what we've done. The Andrill record through here, drilling for floating ice, we recovered much deeper cores, like 1,300 meters of sediment core. Out through over here. But we're trying to produce a composite history of sedimentation across West Antarctica. Another element that the hot water drilling team from Nebraska here did in 2018, 2019 was they penetrated through the Western Arctic ice sheet in this area into subglacial Lake Mercer and wanted to study that particular environment. Here you can see what a typical camp looks like. And this research area for the SALSA project took about 3 years to set up. And this is one reason why we want to make sure that our tools work, because of the advanced effort to put all of this in place. And if our tools aren't the best they can be, if they're potential that they're going to fail, we'd rather they fail in a test facility so we can repair them and fix them, et cetera, rather than try to do it out here because it's just too costly. So maximizing the scientific return, reducing risk, and actually even knowing the rates of drilling, what is optimal, right? Maybe we're drilling too fast. Maybe if we slow down a little bit, we'll save a bunch more fuel. In any kind of planning for something like this, if I were leading the fuel request for this type of project, I would ask for 50% more than what I need, just to make sure I don't have to shut down, et cetera. Do I need that? Can we better constrain what we need in the field for that? So all of these buildings out through here, these shipping containers, they're red because of Nebraska. We own them. This is basically our drilling system, the hot water drilling system that produced that record. And basically we start out by producing one hole, put a pump in the bottom of that, pump that up, drill next to it, make a connection between these two sites to get fluid circulation. So basically the borehole itself becomes our water reservoir. We then keep producing and sending down hot water. Those shipping containers, 2 of them contain 6 car washes, basically, right? So it's kind of off the shelf car washes for pressure and for heating. And that provides the energy to make our way down here into this subglacial lake. We had a really, you might think, well, what are your problems? You're just melting a hole. But we, for example, when we got down to this level right here, we broke through the ice. We didn't know where we were in that level, right? So we weren't sure whether we were in the lake, that we broke through the subglacial lake, or whether we were above it, right? And it's a very difficult to, once you get a hole into a lake like that, to actually widen it, because all your hot water is going up. And if you're too low, then all your hot water is going into the lake. So it would be great to build and test to know and sense before you if there's a water void coming up there. So entering into subglacial Lake Mercer, it was identified as a subglacial lake by satellites, by the SPOT satellite and some others, because there are different parts of the surface of the West Antarctic ice sheet that are actually rising and falling, right? So the top of the ice sheet is rising and falling when the lakes below them are filling and draining. So think of like a slip and slide, right? And you get a whole bunch of water underneath your plastic sheet, right? It's just a bubble of water and it goes. We can actually track, like when subglacial Lake Conway here drains and fills, a little bit of a delay, subglacial Lake Mercer rises and falls as well. So we know where these things are when we penetrated into this one. This is a site we also drilled in 2010. University of Nebraska's drill team were the first people to enter into a subglacial lake and enter into then this much larger, more complex system. And this is a ice rise we're planning on drilling next year. Give you a sense of the scale of these lakes. Yeah, it's about 2 times the size of Lake McConaughey. And some of that may be equivalent to some of the Finger Lakes. But right, so some challenges that we have in this system is there is dirt and debris and gravel in the bottom of the ice, glacial environment. How do we get through that? Because if we're melting a hole through ice, we're making water, right? But eventually, if you're making water and it's all gravelly ice that you're melting, all that gravel is going to stay in the bottom, right? And eventually, you're going to have a big pile of gravel at the bottom of your ice hole. And how do you get that out of there, right? And in addition, we want to sample that because for this microbial ecosystem type approach to this, we wanted to know all the carbon sources, what's coming from the upstream source in to feed the microbes, what's coming from the sediment source, what's coming from the sediment in the ice source. To identify all of those different vectors, we didn't really have a good way to sample that. I want to show you another brief video here, which is about this SALSA project. Here, to give you a sense about just working in the Antarctic environment.
When you have a continent that's almost completely covered by ice, and all that ice has the potential to melt, you certainly want to understand its history.
15 years ago, people didn't believe there was much water under the ice sheet, and nobody really thought there was life.
We're all doing something different, but we all need the same thing. We all need the water, we all need the sediments, and we all need to get through a lot of ice.
Some of the largest lakes on our planet are under this ice.
If we do the best we can, we're advancing science, I guarantee you.
3 a.m. playing with mud, living the absolute dream.
It's a complicated mechanical system that, if it breaks, you're in the middle of nowhere to fix.
You only get one chance.
That is way different than I pictured it.
And everyone thought it was this big, dead, benign block of ice. But there's some big lakes under this ice. And we just have to get there.
So we were successful in getting into that lake. It was difficult. A lot of the systems were breaking. The UNL drill team did a phenomenal job. They were actually, because you don't have a lot of parts. So of all those 6 car washes they're trying to get going, they kept burning starters out for that. So they'd start up one of the burners and they'd have to take the starter off of that, put it on the next one, start up the next one, right? Because you're just in this environment. So how do you make sure that other parts of the system are working as good as they can? We collected a lot of sediment from this lake, and what you're seeing right through here are some, not a very long core, but you're seeing the sediment from glacial conditions, and then you're basically seeing here the sedimentation in that lake. Not so much of it, but each one of these denser layers through here is reflecting a time when the water's flowing faster. So these are the drain and fill cycles, basically, of this lake, and then the sediment water interface was captured right through here. So as a geologist and a paleontologist, I'm looking at whatever is in these sediments. I'm looking at whatever is in these clasts, because these tiny little pebbles and stones are actually eroded by the ice from upstream outcrops, right? So those marine sediments that are reflecting times when West Antarctica was covered by the sea, that history is recorded in all these little stones. And that's my job, is to try to put that jigsaw puzzle kind of together. Got really lucky of finding about a thumb-sized piece of a rock unit that's about 33 million years old. It provides basically the rock or the sediment component of carbon. It's full of these microfossils through here, including pollen and spores and a variety of diatoms of that particular age. But by using this approach of studying the glacial sediments and then reconstructing upstream, if you will, what exists in those drainage basins, right? So we're kind of looking at sampling the surface sediments through here, right, with whatever we're recovering, or drilling next year and the next year. But the sediments that are here are reflecting what is present upstream, underneath the ice, that we don't have a way to get at. If I were to present a summary of all the work that we've done from sites in that area, the salsa ages are here. There's some other ages through here, but what we have at present is a composite history of every green bar through here represents a time. These are in millions of years when there were open marine seas across West Antarctica, right? What we're really still missing is this record up here. There are a couple of sites, Willen's grounding zone, Cam ice stream, where we're going to be drilling upstream B, that may give a bit of a hint about that, but it's really spotty and sketchy. We need to improve on that. Yep. So some of those sites that we have looked at are in these regions, right, through here of West Antarctica. And a big question we have is, and the original assumption was that when West Antarctica deglaciates, as we know it did from the Andril records, does it deglaciate by this ice embayment coming in, and this one up here in the Weddell Sea coming in, or something else? And the models are now really focusing on this area right here, the Thwaites Glacier and the Pine Island Glacier, that this is the area that's going to go first, right? And by looking at the microfossils that we have present over here, we're trying to match that up to see whether or not we can see marine conditions up here of the younger ages when we don't see them over here. So we have some trace of younger ones here, which may be being drained from these areas, where farther inland, we don't see them. So trying to piece that together. I'm going to talk to you about another project that we are hoping to do, and maybe advancing this ice silo, and some other tools that we have would be to drill right in this area, right from the top of the West Antarctic ice sheet, to get directly at this this sediment history through there. So yeah, the Salsa project, we had some challenges. Getting through the lake was one. Getting through the debris that was out here, we weren't able to recover, was another. But great success in all the sampling that we were able to do. A considerable problem with any of this is drilling through the basal debris ice. So what you're seeing right here is the amount of debris, dirt, rocks, sediment, mud in the ice layers through here. This is in terms of meters through here, so about 20 or 10 to 15 meters through here. And there are distinct zones of gravel. I'm really interested in recovering those pebbles, because that's going to be telling me is the marine history up there. But getting into this is a problem. So Jim McManus and Dennis Dooling and myself and others have proposed a new type of drilling tool. And we started to think about this, that we need this tool. It would be a tool that would be driven by the hot water system. It would be a tool that would rotate and be powered to recover those cores, recover the dirty ice core, something we're not able to do adequately right now, but it would be powered by the hot water directly, right? So you could rotate with energy from above, but you don't really know what you're doing, what you're getting at. But we have this pressure, which doesn't attenuate with depth. And the plan would be to use the pressure from that hot water drilling system to either generate electricity in this zone locally, to then power an electric motor, right? To drill and core this. This is standard ice coring technology to recover a core of ice through here, or to use the hot water pressure as well to actually provide the forcing and the rotation for this. And by having the hot water in there as well, we know we were not going to get this drill string stuck in there, because we can always melt our way back out. We went through a conceptual design by the ice drilling program through this, and we're going to propose to do this, to build this with National Science Foundation. As part of our conceptual design review, the other people that were on the review team giving us advice and challenging us for our system here, they also said, okay, let's all do this. The community needs this. And it would be driven by a clean access system here as well, right? So we could go anywhere down there and not be confined by not contaminating this system. But then we said, okay, where are we going to test this? Where could we test it? And we costed out what it would take to take this hot water drilling system to Alaska or to Greenland, right? It was $500,000 just to get it up there, to get the fuel there, to make sure we could be staged to do that, right? And that just seemed like maybe not the best way to go, because even there, if something broke, how do we fix it, right? So then Dennis Dooling, the head hot water driller, he said, well, you know, Dave, there's a big hole in the ground over there by Seward, which we could maybe, repurpose to something like that. So the goal with this tool and others like it, but would be standard hot water drilling, right, to make a hole, but then putting this tool down here and being able to recover through the dirty ice, pull it up, recover that core, go down, drill the next bit, etc. But with this system, we could actually then continue into these subglacial sediments below that, right? Not into the marine sediments directly. And because if we were drilling on the top of the ice sheet, any marine sediments that are down there, they're not being eroded, because from the erosional force, the lateral motion of an ice sheet is based on its surface slope. So if you're on the crest, only the ice is only going down, right? So the goal would be to maybe recover this subglacial sediment. So this is what our challenge was, and our approach to the grand challenges was, where do we test this tool? Where do we make sure it's going to work? Where can we design it? How can Nebraska continue to excel in developing new tools? And that was to find a way to build a column of ice that would be individually refrigerated to basically reconstruct that particular environment. So the site that you already saw in that first video from the Seward site, Seward County Roads Department owns this site. The silo is open. These are some of the original Quonset huts. It's a 20 acre or so facility, but we saw the potential for education and tourism, right? 74 of these silos were built in about a year and a half in result of the Cold War, Cuban Missile Crisis, et cetera. But, museum, education outreach center, Cold War archives and library, meeting space, maker space, ice drilling work through there, et cetera. Lots of opportunities in this grand challenge effort. So this is what the construction site looked like. They excavated out much of the dirt, right? Put it over here, made this column hole through here, tried to keep the water out of it, put the launch control facility in here, and then they buried it all. So you can see there's 12 of these around Lincoln. The one we're focusing on is Seward, because the Seward County commissioners and the roads department are very keen to work with us on this. But this then comes down to this, the concept of this. And these designs I'm showing here were produced by Brian Kelly's architecture design studio students. So he in this course last fall, and it's happening again this fall with a different set of students. It's a 12 credit hour senior capstone course to repurpose this, to design this. And they focused initially on the ice drilling part. This season, this semester, they're focusing on the more on the tourism, the education, the outreach components of this. But it's just great to see that effort. Basically, what you're seeing through here are 10-foot collars, about the A diameter, 10-foot high, 15 of them all stacked up together. Each one of these would be individually refrigerated, going on up And you could essentially make something like marine sediments in the bottom of this one, glacial sediments up through here. You could even have a subglacial lake through here going up into dirty ice with granite and hard rocks, or dirty ice with soft rocks, and then progressively decrease the temperature, make it all colder so the ice gets harder as you go up. So you could custom design whatever you anticipated you were going to need in there, and you could design as you go. Other ways, our tools are really stupid. We're drilling down there with our eyes closed, trying to figure out what's happening, but we could make smart tools. We could make tools that are helping us predict what's going on through there. So one project that I would like to, and did talk to NSF about this, would be to drill from the top of the West Antarctic ice sheet, to go right into the center of this marine basin, but also to recover the history of this area from the ice. So I think this was 10 years ago, the Waste Divide ice drilling program. They drilled a hole right through here to get that expanded record. Of course, there are these much longer records in East Antarctica, but in the lower West Antarctic ice sheet, the tape recorder of time is going faster because there's more snow accumulation, right? So to drill in this area, it's getting a different history of West Antarctica. And they drilled down through to about here. They went back 60,000 years. And of course, as you go deeper and deeper into the ice sheet, everything gets compressed, right? So you're getting a longer record towards the end. They had to stop because if they entered the bed down here, they were going to contaminate it, right? With our system and with this tool, we could continue that record. And if it merited the big NSF investment to get the upper part of this record, right, we could perhaps continue this down through the next glacial cycle through that. So this might be the scientific goal, the mission that is going to get our debris ice tool developed, but also to build the test facility for it as a component of that. And then, right, so to continue that record, and then to continue into the marine sediment history that's down below this as well, getting a unique record from the center of West Antarctica that may be the most complete, right, from direct sediment. And it's also, there are these international regulations from the Scientific Committee for Antarctic Research about governing who can go in there, how do you go in there, how are you, able to get there, policy documents, if you will. It's still developing, but again, if we could get this community to require certification for cleanliness, and our system was clean as well, then that would guarantee business for this project. Shift gears a little bit and just talk about another drilling project in this area that is going not after the ice or the debris ice, but is going after the marine sediments that are in the West Antarctic ice sheet. This is kind of like an Andrill Jr., if you will. It's being led by my colleague and former PhD student, Richard Levy from New Zealand, but you can see all the national investment in here. We have 10 nations that are involved in this project. And acronym here of SWACE2C is sensitivity of the West Antarctic ice sheet to 2 degrees warming, right? So when we get to that record, predicting when we get to that record, what's the ice sheet gonna look like? So we are planning to drill here this year and here next year to get that record and fill in some of that history. The infrastructure of McMurdo Station from the US and Scott Base from New Zealand is here, and there is a route to the South Pole that we'll make use of. So basically drilling from a camp, drilling in the first site through a water cavity and then into the sediments below. This is the New Zealand hot water drilling system. This is the drill rig that we'll be using. It's being tested in New Zealand there. And it really comes down to the question about these numerical models. A lot of this, again, is trying to figure out how can we predict the rate and the size and the timing of changes in the West Antarctic ice sheet. Is the Thwaites sector gonna excavate first? Now, when I said we are currently at 420 parts per million from the Andrill record, I said at 400, right? We've already seen dynamic behavior of the West Antarctic ice sheet, so we are already there. And the scary part about this most recent modeling shows that the Thwaites Glacier excavates out even before that, right? So maybe even at 300 or 350 parts per million, which we saw 10 years ago, right? It's just a matter of when all of this stuff comes into equilibrium, of trying to figure out which sectors are going to go first. So in part, we thought that it was the Weddell Sea or the Ross Sea sectors that we're going to excavate first. It appears that the Thwaites on this sector is the one that that empties first. And again, the target for our adventure here is to drill into the center of West Antarctica, continue the ice core record, and continue then below that with new technology, with new drilling tools, to be able to enter directly into the marine embayment that's right there. Again, because this ice sheet is flat at the top here, there's no lateral erosion necessarily. Everything is just going down. You go away from that crest, and then you get lateral erosion. So to get the most complete marine record of when there was ice sheet absence in this area is going to be in that time. So I think this tool and other tools have a potential to be built and to be tested and designed in a way, if there is a facility, something like this, right, where they can be tested, where they can be built. And Nebraska, by having the tool shop, by having the skills, by having the engineers and the drillers to be able to make this type of an approach go. So anyway, I know it's a big, bold plan. I really appreciate your guys' time. Hopefully you found something interesting in that, learned some things about climate, but at the forefront, this is certainly at the forefront of the technological design to get these records from remote areas with the greatest success we can. Yeah, thanks very much.